Welcome everyone. I'm Dr. Larry Sterna, and in this video I'm going to show you how to calculate the potential around individual charges and the potential energy for a pair of charges. Let's begin. Here are three equations for the x, y, and z components of the electric field. I derived these in an earlier video. We could plug numbers into these equations and calculate those components. But instead of doing calculations, I'd like to consider two important principles that we learned from these equations. The first one is electric field is associated with a change in voltage, whatever direction you're considering, X or Y or Z. Electric field is associated with a change in voltage. The second principle comes from the negative sign in each equation. Electric field always points in the direction of decreasing voltage. Let's consider the field and the potential around a positive charge. The electric field points outward from a positive charge. Remember, the field is in the same direction as the force would be if we brought another positive charge close to this charge. Since the field points outward in every direction, there must be a changing potential in every direction around this charge. And also, since the field points outward, the potential should be decreasing as you move away from the positive charge. Here's the equation for the potential around a charge. That capital V for potential or voltage is equal to the Coulomb constant, K sub E, times the value of the charge divided by R. R is the distance from the charge. I've included a graph there to show you what the potential looks like in the vicinity of a positive charge. There are no numbers on the graph. It's simply to show you the shape of the curve. Notice when R is small, the potential is going to be very, very large because R is in the denominator. For a positive charge, the potential is going to be a very large positive number. As R gets larger and larger, in other words, you get further and further from the charge, the potential gets smaller and smaller. Let's take one value of the potential. We'll call it V sub A at a particular distance R from the charge. If we go to the picture on the right, you see a dashed line labeled V sub A. The potential is going to depend upon the distance from the charge, but it doesn't matter whether you're going left or right or up or down. It's going to be the same at that distance from the charge in any direction. And at a certain distance from the charge, we'll have a certain value, V sub A. Let's go back to the graph. Let's suppose we take another value of potential about twice as far from the charge. We'll call it V sub B. So let's go to the picture on the right. See what V sub B will look like. The dashed line, it's about twice as far from the charge as the previous one, represents V sub B. The potential is the same everywhere at that distance from the charge. Let's consider those two potentials, V sub A, V sub B. If you go to the graph on the left, you see that for this positive charge, VA, which is closer to the charge, is a larger potential than VB, which is further from the charge. The electric field points outward toward decreasing potential. V sub B is smaller than V sub A, so in every direction, the electric field points outward. The electric field depends upon change in voltage. Those dashed lines, one for V sub A, one for V sub B, are called equipotentials. Means everywhere on that dashed line, at that distance from the charge, you have a constant potential for the one, V sub A, for the other one, constant potential, V sub B. Since the electric field depends upon change in voltage, there will be no component of the field along an equipotential because voltage is constant. Therefore, the field lines must always be perpendicular to the equipotential lines. Let's consider the field and potential around a negative charge. Remember, the field points inward toward a negative charge. The field has the same direction as the force would be if we brought a positive charge close to this charge. Since the field points inward from every direction, there must be a changing potential in every direction around this negative charge. And since field points to lower potential, the potential must be decreasing in the vicinity of the negative charge. Here's the equation for potential. Capital V equals K sub E times Q over R. There's the graph illustrating the appearance of the potential. There are no numbers on this graph, but let's think about what the graph indicates. If Q is a negative charge and R is small, R is in the denominator, V will be a very large negative number. That's what the graph is showing. Potential V goes sharply down on the left side of the graph. It's going to a very large negative number. As R gets larger and larger and larger, the potential will approach zero. But since for a small r, the potential starts at a large negative number, as it approaches larger r, the potential increases. As the potential approaches zero, it is increasing from a negative value. Let's consider the value V sub A at some distance r from the charge. We'll place it on the picture to the right. At the distance r from the charge in any direction, the potential will be V sub A. Since it's a negative charge, V sub A will be a negative potential, a negative voltage. The dashed line represents an equipotential. At every point on the dashed line, the potential is V sub A. Go to the graph. We'll take a value of the potential at about twice the distance from the first one, V sub B. Notice V sub B is also a negative number. It's in the vicinity of a negative charge. However, it's larger than V sub A. V sub B is closer to zero. Let's go to the picture. There's the dashed line showing V sub B. Since V sub A is smaller than V sub B, the field points inward, goes from higher potential to lower potential. In every direction around the charge, there's V sub B is at a higher potential than V sub A. Since electric field depends upon change in potential, there is no component of the electric field along an equipotential. Electric field always perpendicular to the equipotential lines. Let's consider what happens when one charge approaches another charge. Suppose we start with charge Q1. At a distance r from that charge, we will have a potential V1 equal to K sub E times Q1 over R. We bring another charge Q2 to a distance r from the first charge. Q2 is now sitting in the potential of Q1. This results in a potential energy given by the formula Q2 times V1. Potential energy associated with a charge sitting in a potential. Notice if you plug in the equation for V1, the equation you'll get for potential energy will be K sub E Q1 Q2 over R. Now let's look at it from the opposite perspective. Suppose we start with charge Q2. At a distance r from Q2, we will have a potential V2 equal to KE Q2 over R. Now suppose we bring a charge Q1 to a distance r from the first charge. We will now have a potential energy from this charge, Q1, sitting in the potential of Q2, given by Q1 times V2. When a charge is located in a potential, it has the potential energy given by the value of the charge times the potential. If you take the formula for V2 and substitute it into the equation, you get the equation of potential energy equal to KE Q1 Q2 over R. We conclude that it doesn't matter which charge you start with. Whether you start with Q1 and its potential and bring Q2, or you start with Q2 and its potential and bring Q1. The potential energy of a pair of charges given by K sub E Q1 Q2 over R. What if you had more than two charges? Well, you would sum up the potential energies one pair at a time. Also consider this formula looks similar to the formula we looked at earlier for force, except two very important differences. Algebraically, force is KE Q1 Q2 over R squared. This is R in the denominator. It's not R squared. But also very significantly, force is a vector. Potential energy, or energy in general, is never a vector. However, there are some similar things you can learn by considering potential energy or force. They do have a relationship. If the two charges Q1 and Q2 have the same signs, either both positive or both negative, they will repel. They will also have a positive potential energy. Therefore, if you move them apart, the potential energy will decrease. The force tends to push them apart because force makes things go downhill. On the other hand, if the charges have opposite signs, one positive and one negative, those two charges will attract. They will also have negative potential energy. As they get closer, potential energy will become more negative, will go lower. The force is attractive. It brings them together because it makes things go to lower potential energy. Let's work a problem now. This will give us an idea what the calculation looks like, what some typical numbers might look like, what the units look like, and we'll solve this in a couple of different ways for practice. Here's the problem. What is the potential energy of a titanium 4+ ion and a chloride ion separated by 217 picometers? Remember, you have to have at least 2 ions to have potential energy. What about that separation, 217 picometers? Well, that's a typical value for a bond length. So that's a realistic number. Second part of the question, or second part of the problem, what is the meaning of the sign of the potential energy? Let's begin with the titanium 4+ ion. The 4+ means that it has lost 4 electrons. The charge of the ion would be 4 times the elementary charge, which is 1.6 times 10 to the minus 19 coulomb. So 4 times that, 6.4 times 10 to the minus 19 coulomb. Let's start by calculating the potential of this ion at the distance 217 picometers. Here's the formula. We have the potential equals the Coulomb constant, 8.99 times 10 to the 9th, times the charge. There's the 6.40 times 10 to the minus 19 Coulomb, divided by the distance from the charge, 217 picometers. Pico stands for 10 to the minus 12. It's simply an abbreviation for 10 to the minus 12. We have to convert to the correct unit, which is meter, so we put in the power of 10. You calculate the value. The value comes out to be 26.5 Newton meter per coulomb. That's a curious unit, Newton meter per coulomb. We could go to a textbook, to the internet, see if that's equivalent to something else, or we simply remember we're calculating potential, which is the same as voltage, so the 26.5 must be 26.5 volts. To calculate the potential energy, we bring the chloride ion to that distance, 217 picometers, from the titanium ion. We have to get the charge of the chloride ion. It has gained 1 electron, so it's minus the elementary charge, minus 1.6 times 10 to the minus 19 coulomb. Potential energy of that pair of ions will be the charge of the chloride times the potential from the titanium ion, the 26.5 volts. The answer is minus 4.24 times 10 to the minus 18 joules. The unit you would calculate would be coulomb volt. We know energy is measured in joules. Notice the potential energy is negative. What is the meaning of the sign? Negative sign means those 2 ions are attracted to one another. Now, let's work the problem a different way, just for illustration. Here is the same problem. We're going to do it again, but we'll do it a little differently. This time, we'll start with the charge of the chloride ion, minus 1.6 to the minus 19 coulomb, and calculate the potential from this ion at a distance of 217 picometers. So here's the potential. We have the Coulomb constant. We have the charge of the chloride, the minus 1.6 10 to the minus 19 coulomb divided by 217 picometers. That's 217 times 10 to the minus 12 meters. The result is minus 6.63 Newton meter per coulomb. Since this is potential, we know it's minus 6.63 volts. Not only is the potential negative compared to what we calculated for the titanium, it's a smaller number. Minus 6.63 instead of the 26.5 for the titanium. Now we calculate for the titanium ion its charge and the potential energy when you bring the titanium ion into the potential created by the chloride ion. There is the charge of the titanium ion, 6.4 times 10 to the minus 19, times the potential of the chloride ion, minus 6.63 volts. We obtain the same answer we obtained before, minus 4.24 times 10 to the minus 18 joules. The minus sign, of course, means the ions are attracted to one another. It doesn't matter whether you consider the smaller ion in the potential of the larger ion or the larger ion in the potential of the smaller ion. The potential energy is associated with both ions, so it doesn't matter which way you calculate it. In this video, I discussed the potential energy and the potential or voltage of charges. Voltage is one of the most important quantities in an electrical circuit. In the next video, I'm going to introduce the capacitor, which is one of the most important components in an electrical circuit. See you there.